Yesterday we defined two new terms in the context of uniform circular motion. Uniform circular motion, by the way, circular motion in which the object moving in the circle, moving at a constant speed. Not a constant velocity, the direction is changing. Constant speed, the magnitude of the velocity remains the same. The first term we defined was frequency. Frequency was the number of cycles per second. In this case, one cycle would be a revolution, so it would be the number of revolutions per second, or the number of cycles per unit time. The symbol for frequency was F. So an equation would have been like this. F is equal to the number of cycles divided by the total time. Now, unfortunately, that equation is not on our data sheet. It comes more from the definition than from a data sheet. It's not really an equation. It's a definition. Number of cycles over the total time. The period, sorry, by the way, what would the units be for frequency? The standard units, that is. Yep. Revolutions per second, RPS, as opposed to revolutions per minute, RPMs, or hertz. Both of those mean exactly the same thing. Period is exactly the opposite of frequency. If frequency is the amount of cycles per unit time, period is the amount of time per cycle. Well, if it's the exact inverse, then the period, which is given by the symbol capital T, is not going to be cycles over time. It's going to be total time over the number of cycles. That's not on our data sheet either. There is, however, an equation that relates the two of these together. T is equal to 1 over F. That one does appear on our data sheet. Period is the inverse of the frequency. Or if you rearrange that, frequency would be the inverse of the period. What's the units for period? The standard units, that is, for period. Oliver, what's the standard units for period? You know this. Don't look it up. Just tell me. Wait a second, he's saying. I can't remember. Wait a second, Tom. Seconds. The standard unit is the second, right? The period of the Earth going around the sun is 365.25 days. So we can measure it in days, or in hours, or in minutes, or in years. But the standard unit is going to be in seconds. Speed, well, we know what that means, right? But in the context of uniform circular motion, we can derive an equation that's specific to uniform circular motion. The distance around the circle once is called what? This is a math thing. The distance around a circle. Circumference. And the equation for circumference is 2 pi r, or as Jazzy said yesterday, pi times diameter. We're going to replace delta d with 2 pi r, the circumference. Well, if we're talking about the distance around a circle once, then we have to have the corresponding time around the circle once. What is that corresponding time called? The time for one complete revolution or one complete cycle. It's called the period. So it would be V would be equal to 2 pi r over t. That one does appear on our data sheet as well. Speed of an object in uniform circular motion is 2 pi r over t. All right, now we did an example yesterday which is pretty straightforward. Probably the most challenging part of this was converting from hertz to revolutions per minute. We simply divided by 60 to get that. And we had a couple questions to work on yesterday. Any issues with these questions? With these three questions that we worked on? Yes? Yeah, absolutely. Number 3, any others? Okay, 3 it is. It says a medical centrifuge is a device that separates blood into its parts. So a centrifuge spins around. You put blood in these vials. They have to be special vials, because if they're not special vials, they'll break in this centrifuge. You get enough force acting on these vials that they'll literally smash. So you put this blood into these vials, then you put it into this centrifuge, and then you spin it around really, really, really fast, a number of revolutions per second. And that causes the heavy parts of the blood to go to the outside. The lighter parts go towards the outside, but not as far. So in effect, what you do is separate components of the blood. That makes sense? That's also used, by the way, when we're creating nuclear fuel, when we're trying to separate one type of uranium from another type of uranium to put into a nuclear power plant, or worse, to put into an atomic bomb. Okay? We use one way of doing it is to use a centrifuge to separate the heavier parts from the lighter parts. The heavier parts go towards the outside. The centrifuge can spin up to 6.0 times 10 to the 4 revolutions per minute, 60,000 revolutions in a minute. What's its frequency in hertz, and what's its period? Well, we know the frequency in number 2 is 6.0 times 10 to the 4 RPMs. We want to find the frequency in hertz, the standard units, and then the period. How do you get that into revolutions per second? What's the conversion between a minute and a second? How many seconds in a minute? Everybody should be answering this one. 60. Good. Somebody knows it. Somebody knows how many seconds in a minute, right, Tom? You're the only one, though, I guess. We're going to multiply or divide. Sorry? We're going to divide, yeah. We got to get less revolutions in 1 second than we get in 1 minute. So it's going to be divide. When we divide that by 60, what do we get? I think 1,000? Is that right? 1,000 revolutions per second, or 1,000 hertz. Now, the period is most easily found by saying 1 over the frequency, 1 over 1,000. 1 over 1,000 is 1.0 times 10 to the negative 3 seconds. So you get 1,000 revolutions in 1 second, and it takes 0.001 seconds to make 1 complete revolution. So it goes pretty quickly, right? It spins pretty quickly. Okay, that's why we're able to separate the components of the blood. Okay, as you're spinning around on an amusement park ride, the same effect kind of wants to happen, right? We want to separate the components of the blood. Well, we don't want to, but nature wants to separate the components of the blood. It doesn't do it, though. Why not? We're not spinning anywhere close to 1,000 revolutions per second, right? If you're spinning anywhere close to 1,000 revolutions per second on an amusement park ride, the least of your concerns is separating the components of your blood. Okay, the biggest of your concerns is probably your brain sloshing around against the side of your head. You'd probably be dead long before you'd notice the effects on the blood. The blood would also leave your brain, by the way, and go to your feet, which would make you pass out before you actually died. So at least it wouldn't be painful because you'd be unconscious. Okay. Is that okay? Who asked me for that question? Kathleen, it's good? All right, excellent. Let's try another one, 5.2, this time on page 251. It says a pebble is stuck in the treads of a tire at a distance of 36 centimeters. I don't like that. From the axle. It takes 0.4 seconds for the wheel to make 1 revolution. What's the speed of the pebble at any instant? Here's my radius. I'm going to make it 0.360 meters. My period here, the time for 1 complete revolution, is 0.40 seconds. I want to know the speed. I want to know how fast it's moving. We're going to say v is equal to 2 pi r over t. It's 2 times pi times 0.360 divided by the period of 0.40 seconds. We end up getting here 5.65 or 5.7 meters per second. I used to have a little bike computer on my bike, just a little $25, basically a speedometer and odometer on your bike. Anybody have one of those on their bike? Yes? You can get them wireless now for $25, or good ones now. Mine was wired, but it was still pretty good. It measured things fairly accurately. How it worked was you put this little piece of it's like a little magnet, okay, with a little kind of spool of wire inside this plastic case on the fork of your front wheel. And then on one of the spokes, you put a little magnet. And you had to put it in the right place so that it would line up. Now, the way that it worked was that every time that little magnet went by that little spool of wire inside that plastic case, it sent a signal to the bike computer. That's it. That's all it did. It didn't tell you how fast you were going or anything like that. It sent an electrical signal every time the magnet on the wheel went past. It sent an electrical signal. Now, all the bike computer did basically was time it. Okay, the bike computer knew how long it took between signals. Does that make sense? Well, the time between signals would have been the period, right? Because the wheel would have made one revolution from one signal to the next. So it measured the period. That's it. When I installed that bike computer onto my bike, I had to put the radius of the wheel. I had to input that. Okay, it couldn't measure it. I had to input it, 26 inches or whatever it happened to be. Now, the bike computer measured the period, and then it simply did a calculation several times per second. It said 2 times pi times the radius of the wheel, whatever the radius of the wheel that I input was, divided by the period. And the period came from the electrical signal that was sent. Does that make sense? Okay, so now you know how that bike computer figures out how fast you're moving. Okay, it's just a simple measurement of time. And then it basically acts like a calculator and calculates the speed from that. Okay, let's take a look at these two questions, please, on page 251 that go along with this, the whole idea of speed here. All right, let's take a look at number 2, everyone. It says, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star called a pulsar ever found. It has a radius of only 16.1 kilometers. I don't like those units. Okay, that might seem like a big number, 16.1 kilometers, but we're talking about a star. Like, that's a small star, right? A small collapsed star. It's spinning at a rate of 716 hertz. Like, it's 16 kilometers radius, and it's spinning around 716 times per second. We don't know what its speed is at the equator. How fast is it moving? If you were standing on this star, how fast would you be moving as you're spinning around? Well, we know that v is equal to 2 pi r over t, and we're looking for v, speed. That's equal to 2 times pi times the radius, which is 16,100 meters, because we always want to be in meters here, right? Let's divide that by the period. Do we know the period? We do not. Let's get it. How do we get the period here? Where's the period come from? This isn't hard. Yep. Time over number of cycles. Yeah, the total time over the number of cycles. We could do that, but we don't know what the time is here or number of cycles. What's the easiest way here, Jazzy? 1 over the frequency. Period is equal to 1 over the frequency. So let's say period is equal to 1 over 716. We get a period here of 0.00139966 seconds, which we're going to turn on and plug into here. Figure out what that is. 2 times pi times 16,100 divided by 0.001 gives me 7.24 times 10 to the 7 meters per second. That's pretty fast. That's pretty fast. That is approaching the speed of light fast. Okay, that's a lot faster than we're moving on Earth right now. Right? Who asked for that question? Who asked that one? Is it good? Okay. All right. 2 more terms here today. Centripetal acceleration and force. Have a look up here, guys. As I swing these keys around my head in uniform circular motion, these keys are moving at a constant speed. Therefore, they're not accelerating, right? If they're moving at a constant speed, not speeding up, not slowing down, then they can't be accelerating. Because acceleration is dependent upon a change in speed, right? Wrong. Acceleration is not dependent upon a change in speed. It's dependent upon a change in what? Yes. Bigger though, change in velocity. Acceleration is not the rate of change of speed. Acceleration is the rate of change of velocity. Now, as I swing these keys around my head at a constant speed, speed isn't changing, but the velocity is. Now, how can the velocity be changing, Tara? Because the direction is changing. Since velocity is a vector, if the direction changes, we don't need the speed to change. The direction changing gives me a change in velocity. Therefore, there is an acceleration. There must be an acceleration as long as the direction is changing. We call that a centripetal acceleration. A centripetal acceleration. Centripetal means center seeking. There is an acceleration. And oddly, that acceleration is actually directed toward the center of the circle. Well, that doesn't make sense, does it? How can the acceleration be toward the center of the circle? It's not even moving toward the center of the circle. How can the acceleration be toward the center? Well, if there's an acceleration, there's also got to be a force. Right? Whenever you have an acceleration, you got a force. Which way is the force acting? Well, what's causing it? What's causing the force? My hand is causing the force, right? I'm pulling on the string that pulls on these keys. Where is my hand as I swing the keys around my hand? My hand's in the center of the circle. Then where am I pulling the keys towards? The center. If the force is toward the center of the circle, and it's got to be because my hand is what's causing the force, then the acceleration has got to be toward the center of the circle as well. So we have two things now. An acceleration, a centripetal acceleration that is the acceleration that is directed toward the center of the circle. And then, of course, we have the centripetal force, which is the force that's directed toward the center of the circle. If you got an acceleration, you got to have a force. If you got a force, you got to have an acceleration. And you're always going to find that the force is in the same direction as the acceleration. So if one is centripetal, one points toward the center, and the force clearly does, then the acceleration must be centripetal as well. It's also got to point toward the center of the circle. There's a lot of places where you're going to see an object experiencing a centripetal force. Every time something moves in a circle, or at least even part of a circle, it's got to experience a centripetal force. Objects want to travel in a straight line. Law of inertia says objects want to travel in a straight line forever and ever and ever until acted upon by an unbalanced force. If they don't travel in a straight line, there's got to be an unbalanced force acting on them. If they travel in part of a circle or a full circle, that force must be centripetal. But now listen carefully to this. The centripetal force is not a fundamental force. It's not a force that exists on its own. It's always caused by something else. As I swing the keys around my head, there is a centripetal force acting on these keys, but it's caused by my hand and the tension in the string. As the Earth revolves around the sun, there's a centripetal force acting on it, but it's caused by gravity. As the electron orbits around the nucleus of an atom, there's a centripetal force, but it's caused by an electric force. As your car goes around a turn on the road, there's a centripetal force toward the center of the circle, but it's caused by friction between the wheels of the car and the road itself. Centripetal force is always the force that's acting toward the center, but it's always caused by something else. In fact, sometimes we say it's just renaming another force. The force of friction pushes the car toward the center of the circle. Let's call the force of friction the centripetal force. The string causes the keys to go in a circle. Well, let's call the force of the string the centripetal force. Gravity causes the Earth to go in a circle. Well, let's call gravity the centripetal force. Okay? Give you a couple equations here. The centripetal acceleration, at least, what do those two little vertical lines mean? Absolute value. The magnitude of the acceleration, this equation won't give me the direction. That's okay, because we already know the direction. It's toward the center of the circle. We don't need an equation to tell me direction. We know which way it is all the time. It's toward the center. The magnitude of the acceleration is v squared over r. What does v stand for there? What's v stand for? Speed, not velocity, speed. And r stands, of course, for the radius of the circle in meters. Well, centripetal force, we're also not going to get the direction of the force, but that's okay, because we already know the direction. It's toward the center of the circle. Centripetal force, well, would be m times a. But what's the acceleration? V squared over r. So centripetal acceleration, v squared over r, centripetal force would be m times v squared over r, m times the centripetal acceleration. Again, it's that force that always acts toward the center of the circle, but really it's just renaming the other force that caused it. It's renaming the gravity force. It's renaming the force of the string, or renaming the force of friction, or whatever. It's calling it something different and then applying a new equation to it. Now, when the object that experiences a centripetal force, the object that's moving in a circle, for whatever reason has the centripetal force removed, we know, just like that cat video, the cat on the fan video that I showed you the other day in class, we know that the direction of motion, the subsequent direction of motion of that object, will be in a straight line at a tangent to the circle. A tangent kind of means skipping off. It doesn't go out like this. If the object right here all of a sudden has the centripetal force removed, it doesn't go out like this. It doesn't go down like this. An object that's going in a circle is really just at any given point going in a straight line. As soon as we remove the force that's keeping it from continuing to go in that straight line, it will once again go in a straight line. In other words, if we remove the centripetal force of the object right here, it's going to go right here. If we remove the force right here, then it's going to go this way. Newton's first law tells us that. An object in motion will stay in motion in a straight line until acted upon by an unbalanced force. As long as the centripetal force is there, it's going to go in a circle, not a straight line. But as soon as it's gone, it's going to go in that straight line. Let's do one example today, and that'll be it. 5.3 on 255. It says a DVD disc has a diameter of 12 centimeters. We don't like centimeters. Okay, so let's circle that. A rotational period of 0.1 seconds. What's its centripetal acceleration at the outer edge of the disc? We have a diameter of 12 centimeters. That means we have a radius of 6 centimeters, 0.060 meters. And it has a rotational period of 0.1 seconds. That's big T, 0.100 seconds. What's the acceleration at the outer edge of the disk? Well, acceleration is delta V over delta T, but that's not very helpful to me right now. Acceleration in the context of circular motion is V squared over R. That's much more helpful. The only problem is I don't know what V is. So let's find it. Let's combine what we did yesterday and earlier today with what we just did. 2 times pi times 0.060 meters. divided by the period of 0.100 seconds. That gives us 3.76991 meters per second. Plug that in here, 761,991 meters per second. Let's square that, and let's divide that by 0.060. We do that, we end up getting 236.87 meters per second squared. Round that to 3 digits, I should say. We get 237 meters per second squared. What's the acceleration due to gravity? 9.81, right? About 10. This is about 24 times gravity. That's what we call a g-force. When you experience 1 g, that means you would experience an acceleration of 9.81, or about 10 meters per second squared. Okay, if you're, say, a fighter pilot, and you're pulling a tight turn, and you're pulling 5 g's, then that means you're accelerating at a rate of about 50 meters per second. You will, on the Mindbender at the end of this month, experience at the highest point about 4.6 g's. That means you will feel about 4.6 times heavier than you really are. If you weigh 150 pounds, then you will feel like you weigh, for a short period of time, over 700 pounds. You will be accelerating at about 45 meters per second squared. This is 237 meters per second squared. If you experience that acceleration, you would experience about 24 g's. You would survive for maybe a second or two. Then the blood would all leave your brain. That would be it. The most we can experience for a sustained time, more than a tiny fraction of a second, would be 5, 6, 7 g's in extreme cases. Fighter pilots might experience 7 or 8 g's. We'd pass out probably long before that. That make sense? All right, here's your homework for tomorrow, page 255, the practice problems 1 through 3.